I want to take a look at, before we change the decision tree classifier, what is currently doing a little bit more. Now, first of all, if you may have gotten different scores than me, okay? And the reason why is because when a decision tree is creating these splits of the data, there's enough randomization there and enough options that it is actually going to build differently different times. So if you run it again and again, you can see now I got 80%, and now I get 76%. And I think you should be seeing scores within that general range, okay? It doesn't mean that it's like 75 or that it's 80. It means that, it's probably somewhere in the middle, okay? So you can run that different times to get different results, which will give you a better sense of sort of what the model is actually doing. You can put a random state up here and always get the same result, but I think there is more value in seeing the difference in the results. Next, how do we figure out what it's actually doing? Well, if we put some code in here and we want to check the, let's go to model dot, what are the different options? And we look at the parameters. So we see this get params option. And if we run this, it's going to show us what the different parameters are. Now, max depth, the number of questions that it asks, is set to none, which means it will ask as many as it can until it finds convergence. And I want more. I want to know what it actually was for the model. Now, you may have seen up there, in addition to model.getParams, there was a model.maxDepth. And so it seems like, oh, does that do it? Well, if we put in the max depth, it doesn't actually do anything. And so I looked this up in Stack Overflow and found the question, basically, how do I find the depth of a decision tree? And they mentioned that it's set to none, right? I love using Stack Overflow to try to find answers to specific questions that I can't find on my own. And here someone shows it's kind of unusual. It's there within the underlying tree object. So it's not working without, okay? You can see it's got this dot tree underscore in there. So if we do this in combination, okay, so this one is not working. So let's change it. From sklearn, import tree, and then we have our model, and we do dot tree underscore dot max depth. You can see there it's showing as an option. And now if we look at that, we can see that we get 8, and show what that's telling us is it's basically splitting the data 8 times before converging upon kind of optimal results. And so what the max depth does in this case is it can be overfitting the data. If you lower the max depth, stop building the tree after asking less questions, it can potentially generalize better to new data. And that's what we are going to explore right now. We are going to change the max depth, and let's try something less. Like, let's try to cut it in half. Okay, what's going to happen here, it's not going to be as precise perhaps, but it might generalize well to new data. I don't actually know. In machine learning, you want to try things out and see what you get. So I change the max depth and I see what is the test score I get, and it's about the same. It's 77%. I could run it again, 76, not that different. What if I go lower? What if I go like down to, say, something like 2? What type of score will I get? Okay, 69%, so maybe a little less. So in this particular case, there's not enough convergence. It's splitting too early. Well, you can play around with this and see. And look at this. I go to 5 and got the highest score yet. So that's kind of strong, and I get a great score again. And so this is sort of counterintuitive perhaps initially, but what you can see is that just from this one parameter, the depth of the decision tree, you can actually reduce overfitting and get it to generalize better to new data. Now, decision trees are loaded with parameters, and so you see up here some of them. This is not a lesson that we're going to go through all of these. We will be looking at different trees and tree ensemble models, and we'll start to learn, more about, some of these different ones. But you could try like one of these, like let's consider min samples per leaf just to try another one. So what does this tell us? The minimum number of samples required to, min sample split leaf here. The minimum number of samples required to be at a leaf node. Those are the answers, okay? And what the idea here is it's going to keep splitting until you get some minimum number. Now, let's go over what it would mean if all of the leaves were 1. Okay, well, if you've got 300 rows, what that means is you're asking enough questions to split the data, so many times that you get that perfect prediction, because each individual sort of row goes down the tree to its own individual leaf. So of course, then you're going to get perfect predictions. In an optimal world, if we go back to Python, it was saying it split the data 8 times. Well, what is 2 to the 8th? You can't always get perfect predictions depending on, how you're splitting the data, but you can see that it's 256. And so it's actually close there to sort of having individual leaves. Okay, so what this tells you sort of, if you had 256 rows and there were optimal splits, 8 splits would be enough to get unique predictions. And so you can in fact change, we could try to change the min samples leaf. Okay, I think I'm going to leave this up because the score, that's the best score we've seen. And come back down here, put in the min samples leaf. Now what's interesting is min samples leaf and max depth can kind of work together, right? Because, in some, like they affect each other. And so the default is 1. And if we say, well, I think, we want to increase this, right? What are the minimum samples for a leaf? So we're not going to let it go down to 1. What if we just say, well, you've got to have at least 2 in your results? I'm not expecting much of a change, but that could be a small change. Let's see. It actually goes down. That's sort of interesting. Let me show you, though. You can sort of use these in tandem. Like to generalize, well, I think 2 is, I think you want to go higher. Like what if we tried 4 and 4 and we say, okay, we're going to force sort of more generality by cutting this down to 4, but then maybe we send this one back up and we'll say we'll allow for a greater depth. What do we get? 78.9. You can just kind of play around actually. A little syntax error there and see if you can get better results. And you can see up front it's sort of hard to just do better than the max depth of 5. You can even try min samples leaf alone and see what kind of result you get. And you can see that it's not making by itself too much of a difference. And you can also sort of gauge, well, is this really like an optimal way of doing this? No, there are better ways, which we will get into later, but there are a couple of parameters, and you can certainly look at the documentation and look at others to work on modifying your data. So max depth is probably the most important one. And another thing that's sort of interesting here is the splitting of the data, because there aren't that many rows. So I tend to often leave the split as is, like with the 80%. And if you come up to the documentation, shuffling true is good. So the train size and test size, well, you can set one of these, right? It's telling you the test size should be between this. You would think that the train size would know if you set the test size what it should be. It says if none, the value is automatically set to complement the test size. And so you can, well, it says none here, but I can tell you the default is an 80-20 split. So let's set up the test size, okay, and modify it. So we'll go back to the coding notebook. And what I'm going to do is actually, again, copy the code because I want to preserve it, as it was. And we'll come down, do it here. We'll set this up. And the first thing I want to do is simply look at, we'll take off this min samples leaf. What effect a change in the splitting of the data does. So if we have test size, okay, maybe let's go with instead of, we want, I think, basically a larger training size, right? Because, there's only 300 rows. So if we have just like let's try 0.10% of the data as our test size. And let's see, without making any changes, what type of result do we get. Not something that was better, okay, but it's training on more data. And I would also caution you at this point, it's not simply about getting the best score, because you saw at the top, right? You can get a perfect score if you if you score it on the training set. You want it to make sense with your data. So training on 10% is only 30 rows. That's not ideal for sort of a training set. I think honestly 0.12 and might be sort of like a right amount. Get a little more, and that's sort of interesting. It could be luck here. Yeah, see that it changes. Why the drastic change? Train test split has its own randomization built in, like how it's choosing it. And so, let's come down here, and you can see, it's just wildly different because we also have a lot less that we're training on. Now, let's sort of work within the parameters that we've been working with. What if we set the max depth equal to 5? Now, in this case, it's not showing as much improvement. Same thing with 4, and we could even try it in conjunction with min samples leaf, and we get something like, I don't know, let's try 4 again. And you can see, okay, well, that's better result. And so we're kind of working toward better generality. I'm going to pause here because decision trees are not sort of, even though they're incredibly robust, we're going to see better models that include them a little bit later. But this is sort of the beginnings of what's called fine-tuning your data. And down the road, we will look at optimal methods for doing this.